Compounds with identical molecular formulas that differ in their physical and chemical properties are known as isomers. And isomers that differ in their connectivity are known as constitutional isomers. Let's take, for example, pentane. Going back to our previous lesson, we know that pentane is a 5-carbon straight-chain alkane, and straight-chain alkanes, if they have 5 carbons, will have 2n plus 2 hydrogens, so 2 times 5 plus 2 is 12. And if you look at pentane, isopentane, or neopentane, each will have the molecular formula of C5H12. But what we can notice about these 3 compounds is that each differs in its connectivity. Smaller groups of atoms that are connected to a much larger chain are known as substituents, and any alkane that is a substituent is known as an alkyl group. Based on the different constitutional isomers that are possible that we saw in the last slide, we could assign different names to each of these alkyl substituents. The prefix iso means the same, and I like to think of it as an isosceles triangle. So notice that anytime we have a carbon group that on the end has 2 methyl groups on each end, it will be known as an iso-substituent. And since this alkyl group right here is composed of 3 carbon atoms, it is known as an iso-propyl group. If we move on to the 4-carbon alkyl substituents, this is where the naming gets to be a little bit tricky. We've already learned how to classify carbon atoms as being primary, secondary, tertiary, or quaternary, and this all depends on the number of other carbon atoms that our specific carbon of interest is connected to. Take, for example, sec-butyl. We can see that the first carbon off of the main chain is connected to 2 other carbon atoms, hence the name sec for secondary, and the name butyl simply refers to that this substituent is composed of 4 carbon atoms. But what happens if the main chain is another carbon atom? Does this change the name of the sec-butyl group to maybe tert-butyl? And the answer is no. Classification of alkyl substituents depends on the number of carbon atoms that are within that substituent itself, and not what atoms are located in the main chain. If we look at the isobutyl group, as I explained before, we're going to look for a carbon atom that has 2 methyl groups on each end of it. And now if we look at a tert-butyl group, just as in the case in sec-butyl, we're not worried about this parent chain. All we're really worried about is how many carbons within that substituent are connected to this first carbon coming off of the main chain. If we move on to the 5-carbon constitutional isomers, we could see that isopentyl, once again, we could see that just like in isosceles triangles, it has 2 sides that are the same, and those 2 methyl groups that surround that last carbon atom. And neopentyl can be identified through recognizing this group here, a 5-carbon substituent with a carbon in the center, surrounded by 3 methyl groups and a methylene group. And finally, the tert-pentyl group refers to this first carbon coming off of the main chain, and it being connected to 3 other carbon atoms. If we replace the squiggly line representing the main chain with a hydroxyl group or a halide group, we could see how many compounds derive their names. A n-butyl alcohol involves a butyl group connected to a hydroxyl group, whereas an isobutyl alcohol involves a butyl group, only it's isobutyl because we could see that same functionality that's common to all iso groups. We could see that sec-butyl chloride has a secondary carbon connected to the chlorine atom, and we can see that tert-butyl bromide has a tertiary carbon connected to the bromine group. So even though we haven't directly covered specifically how to name any of these compounds, based on your understanding of how to classify certain atoms and how to name alkanes and their isomers, you'd be able to interpret each of these structures based on the name that is given.